Hi, in this video, we will explain how to design a state feedback controller with the help of Matlab. Now, to begin with, why we need a controller? Often the dynamic of the system cannot be changed by the designer to improve the system performance. So imagine you have a system, and that system doesn't follow the desired performance you want. So all we need is to design a controller. To generate a control law, you enable the system to achieve that desired performance. And in this video, we're going to explain how state feedback controller make the system follow the desired performance. Now, in order to design a controller, we need to have a mathematical model of that system. So in this video, we will assume that you have a background about state space model of the system, because based on the state space of the system, we will design the state feedback controller. Now, for a quick refresh about the state space, and we are focusing on linear time invariant continuous system. Now, the two equations of the system based on state space model is the dynamic of the system, which is x dot ax plus bu, and the t just representing that this is changing with time, and the y is c multiplied by x plus du. Now, if we want to have representation of that two equation, we could say like this is the x dot, and if I put integrator, I will get the x, and if I multiply this x by a, I will have the first term of the x dot. Now, if I have u multiplied by b, now this is what I get x dot. Now, in order to get the y, all I need is multiply x by c and u by d and sum both terms, and I will get y. Now, x dot is the derivative state of the system, x is the state of the system, u is the control input of the system, and y is the system output. About the matrices, like A is the dynamic matrix of the system, B the input matrix, C the output matrix, and D is the feed forward matrix. Now, to begin with, let's assume we have two systems. These two systems, we will see how we could implement these two in the Matlab and what the difference between this system and this system. Now, in order to check the performance of the system, we have two problems. The first one is the regulator. The regulator is, imagine that your system have initial condition or just get any disturbance. So all we need is to return the system to its original. So we need to improve the transient response, the shape of the response, to guarantee the system go back to the stability. So this is what we call the regulator problem. Now, the other problem we have is the tracking problem. Now, the tracking problem, if we want to follow a reference input with zero steady state. Now, let's go to the Matlab. Let's see how we could implement the state space of the system, and we check the performance of that system. Now, to begin with, this is the Matlab. I already write the code, so I'll just explain it. Now, we begin with CLC to clear the common window, clear all, so we can clear all the values, and close all, we close all the window in the Matlab. Now, this is the time of our simulation. Let's start by typing the state space model of the system. So this is the state space of our system. This is the dynamic A, this is B, C, D. So all we do is just typing A, B, C, D, and then we go with the code SS, means state space. So we just say G open loop, which is the system in open loop, state space, we use the A, B, C, D, which is the parameter of the system. Now, all we need is to check the pool of the open loop system of that system, which without any controller. So we go with eigenvalue of the matrix A. Now, I just will remove the semicolon to see the pool of the system. In order to investigate the initial condition of the system, all we need is to write this code. Now, we have to have the sampling of the time. So we have sim, which is the total time, 10 seconds. Now we sampling that time every 0.1. Now U is the controller or the reference now, the reference that of the system. Because we're checking the initial condition, so we will put it like 0. And then we say, because we have two states, the first state is 0.5 and the other state, which is just 0. And to simulate the output, we just say y LSIM. This is the Matlab command to simulate the linear system based on the G of the system. So we just put the open loop of the system, the output of the system, which is 0, the time, and the initial condition. Now we will upload the system. So we just have the time of the system, the output of the system, and all remaining is just for the plotting. Now we will investigate the unit step of the system. So also we divide the system, the time. We have the output, which is now 1, because we need unit step response. And we have 0 initial condition. And we also find the y by using it LSIM. And we plot this, the second one, which is represent the unit step. Now in order to see the output, we just hit run. Now we could see this is our system. This is the first case, which is the initial condition. We start from 0.5 and then we get to 0. And this is the step input. As you can see, the system have little overshoot, and then we settle down with like 0.3. So there's error steady state of the system. And if we check the pool of the system, you can say the pool of the system like is stable. Now if we change the dynamic of the system, so instead of have -3, we just put 3, -2, we put 2. Now we will see the system become unstable. So as you see, the system is unstable. If you check the pool of the system, you have 3, which is unstable pool, need to be controlled. So all we do now is let's go to see how we could design a state feedback controller of that system. Now, in order to design a state feedback controller for the system, there are two conditions need to be available in that system. The first one, the system should be completely state controllable, which means the control law U able to influence all the state of the system. And the second condition is the state variable are measurable. So all the state should be measured. Like for example, there's a sensor, read all these state and feed it back to the controller. Now, if these two conditions have been proven, let's go to design the controller. Now, because we say there are two types of the problem, the regulator and the tracking. In the regulator, we need to prove to guarantee the stability of the system, and we need to shape the transient response. So there are two techniques we could use in the state feedback controller. The first one is the polar placement, and the second one is the linear quadratic regulator. And we will explain both of them, how to design them. However, with these two techniques, sometimes there is offset when we try to tracking, follow the reference. Now, in order to remove this offset and we get 0 steady state error, even we have to put a forward gain or we added the integral action. Now, let's go to design the control law in the state feedback controller for the regulator and tracking problem. The control action will be computed based on the state of the system and the reference, and it will take the form U, which is the control law, is the forward gain KR multiplied by the reference minus the feedback gain matrix KS multiply KX multiplied by the state X. Now, if this is our system without any controller, with the controller will be like this. So the state multiplied by the gain Kx and the reference multiplied by the forward gain Kr. And this two term will be the control law U. Now, if we go back to the X dot and we say it's A multiplied by X plus B multiplied by U. Now, if we substitute this U in this U, we will get this. So this U will be substituted by KR multiplied by R minus KX multiplied by X. Now, if we rearrange the equation until we get this, so we will have like A minus B multiplied by gain KX all multiplied by state of the system, and B multiplied by KR with the reference input KR. Now, if we compare these two with the first one, we will see that the A open loop is the only A, but with the closed loop, become A minus B multiplied by the Kx. Now, as we said in the beginning, we cannot change the system. Uh, we cannot change the system, so we cannot change the A and the B. We cannot change them. But now the A closed loop has been changed with the gain. And the same thing with the B. So the B open loop is the B, and we cannot change the B. But if we multiply B by the gain KR, now we could have the new B, which is follow our desire. Now this is the two, which is the A closed loop and B closed loop, are the new system with the feedback controller. So now, if we go back to the dynamic of the system and the control law, now to design Kx, how to find the value of Kx, we say that there are two techniques, the pool placement and the LQR. And to design KR, we will use the form. Now let's start with the pool placement technique. The concept of pool placement is to locate the closed loop pool of the system at the desired location. So imagine you have this pool of the system. This is the real and this is the imaginary, and this is the open loop pool of the system. So as you can see, for example, we have one unstable pool. So the basic idea of the pool placement is to move this pool to the new location, which is our desired location of the system. Now, if we go to the closed loop A matrix of the system, is the A open loop minus B open loop multiplied by the gain, feedback gain. So as we said that A, we cannot change the matrix A and we cannot change the matrix B. So by selecting the base K of X is the key point to select this K so we can get the desired pool. Now, how to get the desired pool? It depends on your experience with what the best place of the pool in order to get a response. So for example, if you have imaginary, you know that you will have like oscillation of the system. And as you go far away from the original, from the zero, your system is more stable. So let's go to the Matlab and we see how we could design the state feedback controller based on the pool placement. Now I already type all the Matlab code. I will just explain what the code. Now in the beginning, we see how we could input the state space of the system and we check the pool of the system, and then we simulate the initial condition and the step response of the system without any controller. Now in order to check the controllability of the system, we have this code, rank, the controllability, we put A and B. If the rank of the system equal to the order of the system is controllable. So if we run the code up to this, and we see what? Now, you can see that the rank of this controllability is 2. And because we have 2 poles, so the system is second order. So because the order of system equal to the rank of this matrix, we can say that the system is controllable and it's okay, we can design a state feedback controller. Now, for the pool placement, as we said, we select the desired pool. So let's say the desired pool is -8, -6. You can choose any pool you want. Now, the command we use to get the gain, which is make the pool is -8 and -6, is a place. So we say that Kx, which is our gain matrix, place A and B and the closed loop pool, which is we selected before. Now, if we want to check, so we will calculate the new A matrix, which is the closed loop, A closed loop, which is, as we said, the A minus B multiplied by the gain matrix. Now, if we check the eigenvalue of the system, so we will run through the system up to this point, we will see that the eigenvalue of the system is equal to the pool, the desired pool. So we put the desired pool -8 -x. Now, the eigenvalue of the closed loop A is -6 -8, which is the same desired pool we want. Now, after we design the gain to obtain this pool, we could say that the new system now, which is the A closed loop and B, C, D is the same. Now, if we check the initial condition of the system and we check the step response of the system, we will see, like for example, in the step response, we put 1. So we need unit step. But the problem is you will see that the system have offset. So if we run the code, now this is the system. This is the system without controller. And this is when we put the controller. So for example, we remove this undershoot. And the response is better than in the without controller. But the problem is with that there is a lot of uh, there is a error steady state in the system. And how to remove this error steady state? We have to put the forward loop. Now for tracking, the code we use is that to remove this offset from the system, we have the DC gain. So our forward controller is 1 over the DC gain of the system. So for example, if you multiply 5 by 1 over 5, so 5 will cancel out, and you will see there's no any offset. So the basic idea of the DC of the forward gain is to have the KR is equal to the 1 over DC gain of the system. And once you get this KR, you just have the B closed loop, which is the forward gain KR multiplied by the open loop matrix B. And then we will check the system again with the Kx, which is new A and new B. And we check the initial condition and we check the step response. Now, if we run the whole system, so now this is the system without controller. This is the system with just pull placement, and this is with the pull placement and forward gain. Now, this is the system without controller. As we see, you have overshoot. Now, we remove the overshoot, which is good, but the system still have offset. Now, for the regulator is okay, but for the tracking is not okay. Now with the DC gain, we can have the system as we want. Now, if we check another system, so let's say our system is not stable. Now we check the system which is not stable. Now this is an unstable system. So if we run the system, so this is the system is unstable. With pole placement, we convert the unstable system to stable system, but we still have the problem with the offset. Now with the forward gain, we could have the system like was preference and initial condition. Now as you can see now, the system is very fast because the place of the pool is -6 and -8. Now if we change these two pool, like for example 2 and for example 3, you will see the system will become slow. So as you go far away from the original, your system is very fast. But the problem is, if you have system very fast, you need to have a control law. You need to enlarge the control law in order to obtain the response you want. So in the pool placement, you can't change the pool of the system, but you can't control the action law. And that's what we will see in the LQR, the Linear Quadratic Regulator, that you have the ability to choose between the response of the system and the control law of. Now we will design a state feedback controller based on the Linear Quadratic Regulator. As we said in the pool placement, the basic concept of the pool placement is to select the pool, the closed loop pool. And based on that, we will find the K, the matrix feedback gain K. Now, in the linear quadratic regulator, the idea is to find the optimal control law U. Instead of just having any U, now we find the optimal U who could achieve what you want as improve the performance, but in the same time, we find the minimum U. The minimum U will achieve that better performance. And we will not go through the mathematical model how to find this by minimizing the index J, this one, because we will use Matlab. Just command in the Matlab and we will find the solution. But the basic idea of this matrix Q and R is adjustable matrix. Now, if we put more weight on the matrix Q, which means our response is more important than the control law. So we don't care about control law, we just care about the response. Now, if we put more weight on the R, which means we don't care too much about the response, but we care about the U and we need it very small. Now, let's go to the Matlab and we see how we could perform the LQR on the Matlab. Now, as we said in the beginning, this is the state space of the system. And we check the eigenvalue. This all we go through this in the beginning. Now also we check the controllability, which is we know that it's already controllable. Now the thing is changing between the pool placement and the LQR is we have to calculate the Q, which is the adjustable, and it should be equal to the A matrix, which means 2 by 2, and R, which is equal to the number of input, which is one input. We have just one U. So for example, we have the same weight, 1, 1, and the R with 1, which is just adjustable. You can choose any number. Now we find the gain by using LQR. Now in the pole placement, we use command place, but in the LQR, we use LQR, and we give him the A and B and the Q and R, and it will give you the gain, K. Now the A closed loop is A open loop minus B open loop multiplied by the gain. Now we can check now the eigenvalue. So if we just run through this, now we don't know what the closed loop. In the pole placement, we know what's the closed loop pool, but in the LQR, we don't know. So for example, based on this selection, let's see what the closed loop. Now you can see that this is the new closed loop. So this is the open loop. This is the new closed loop based on this. So if we change the system, let's say we put too much weight on the response and we don't put any weight to the control low, and we just run the system again. Now look, this is the new pool, which is, as you can see, -1 and -300, which is mean we give too much weight to the pool, so we need the pool to go far away from the original. Now if we do the, like I put here 0.01, let's say 0.01, and I put here, so now I put too much weight on the control low, but not too much weight on the response. Now you can see your pool is just -1, so which means that your response is not like fast as in the first case. Now after we calculate the new system, we will investigate the initial condition and the step response. Now again, we will have offset. So in order to remove the offset, we will find the KR, which is the forward gain, which is 1 over the DC gain of the closed loop, and we multiply it by the B to find the new B, and we find the new system, the new closed system with the feedback gain and forward gain, and we check the initial condition, and also we check the step response. Now we will start from the stable system. So this is stable system, and let's say we put weight on the response. So now I will, okay, let's see the system when we put not too much weight on the response and too much weight on the control action. Now if we run the code, now as you can see, the system have overshoot and very slow because we put too much the system. So this is the system without controller. This is with the just linear quadratic controller, and this is with the feed forward gain. So here we have offset, we are not reaching to the 1, and here we are reaching to the 1, which is the reference, our reference. Now if we just change this to 100, we say here's 0.001. So let's see how the response will be. Now look to the response, is without overshoot. So this is the response without overshoot. Now if we just say okay, 1, now we have a new response. Look, it's very fast. So it depends on how you select the Q and R. Now imagine we consider the system which is like, so this is the system unstable. So let's see, we run the code. Now as you can see, so the system in the beginning is without control, it's unstable. Now it's become stable with the LQR, but we have too much offset. Now with the forward gain, you can see that the system has become okay. Just follow the reference as we want. Now in the last section of our lecture, we will see how we could design a state feedback controller with integral action. So instead of having the feed forward KR, which is multiplied by R, we need to integral the system. Now, the new structure of the system become like this. Now we have R, and this error will be integrated. So if we go back to the dynamic of the system, which is x dot equal to the AX plus BU. So this is the original system. Now we're having a new state, which is E. Now the E dot is R minus Y, and Y is X multiplied by C. Now we need to edit this new state in our dynamic of the system. So we have a new state space. X dot represent the original state of the system, which is the same like X. And our example, for example, was 2. Now with the E, now we have 3 states. So we have a new state, which is E dot and E. Now in order to develop the state space, the relationship between X dot and X is the same A. But the relationship between X dot and E, this is the X dot and this is E, there is no relationship, so 0. The relationship between E dot and X, so this is E dot and this is X minus C. But the relationship between E and E dot is 0. So there's no feedback like here, like you have X feedback with A to the X dot. We don't have any feedback, so it's 0. The relationship between X dot and U is B. But between the E dot and U, there is no any relationship, so it's 0. Now we have a new term, which is R. So we have to put R also. What the relationship between X, which is the state of the system, derivative state of the system, and R, so this is R and this is the X dot, is 0. And I put it like this, 0 sub X, which means we have to put 0 in the number of state of the system. So for example, in our system, we have 2 states, so I have to put 0, 0. Now the relationship between E dot and R is 1. So this is the new dynamic of the system. Now we will call this X dot sub E, and this A sub E, and this state of the system, X sub E, and this is the new B sub E, and this is B sub R. Now the new X dot of the system, the dynamic of the system, is X dot sub E, AX multiplied by X sub E, and BE multiplied by U, and B sub R multiplied by R. Now our controller is R minus K, and here I put capital K, X sub E. Now the new K is contain all the gain matrix of the system with the addition of a new state. So it's like the previous K with the new K, which is belong to the error. Now if we substitute this U in this equation, we will get this. So just substitute the U here. If we arrange the equation, you will get the following. Like X dot sub E, you have AX minus K B sub E all multiplied by X sub E, and BE plus BR all multiplied by R. So now this is the A and B of the open loop system, and this is the A and B of the closed loop system with the integral action. Now how we could find the K? This is the only variable we have in the system. The remaining is like the same, A and B, which cannot change it, and C also. We cannot change A and B and C. So the only variable we have K, and we can use the pole placement and LQR to find this K for the state of the system and also the integral part. So let's go to the Matlab to see how we could implement the state feedback controller with the integral action. Now this is the system, the open loop system, and this is the simulation of the system without controller. Now this is the new part of the system. Now how we could calculate the A, the new A? Now we have to calculate the new A with the integral action. So it's the same A with C and 0, 0. So all we do is A, 0, 0, C and 0. So this is the new A with integral action. B is the same B with just only one zero. So B is the original B with 0. And also the C have now a new variable because we have 3 states, so we have to put 0. So this is the new ABC with the integral action. Now, if we design based on the pole placement, so this is the pole placement. Now, the selection of the poles, it's up to you. I will select like -2, -3, -6. You can change it any pole you want. Now the KX, now we put AI and BI, which is the A with integral action and B with integral action, and the pole of the system. And now we have 3 poles instead of 2. And we will calculate the A closed loop, which is AI minus BI multiplied by this X. This is the new A with the closed loop, with the controller, with the integral action. Now, we can calculate the eigenvalue of the system to see the new pole of the system. Now, we have also to edit the BR, which is, as we said, 2, 0, and 1. So this is the 2, 0, which is the 2 state, and 1 for the error. Now, the B, the new B, the closed loop B, which is BE plus BR. So this is BE with the integral action, and this is the BR. Now the new system is A closed loop, B closed loop, C integral, and D, because still we just have one input, so it's just D. Now if we simulate the system based on the pole placement, we will see that the system now for the initial condition and the tracking the unit step input, there is no offset in the tracking. So we don't put any feed forward gain, but with the integral action, we solve this problem. Now, if we hit run, so this is the system, and this is the system with the integral action and pole placement. As you can see, this is the initial condition, and this is the tracking. Now, if we change the dynamic of the system to nonlinear, to any stable system, so now the system is unstable, and we can see that. So this is the system unstable, but with the controller. So this is the initial condition, which is stable, and also this is the system when I put unit step input, and this is with the tracking problem. So this is the initial condition, and this is the regulator, and this is the tracking. Now this is the system with the pole placement, and you can see now. So this is the new A with the integral action, and this is the B and C. So this is the gain Kx. So this is for the 2 state, and this is for the E. And this is the new A, the closed loop, and this is the pole of the system. This is the pole of the system, and we see the response of the system. Now, if we would like to design it based on the LQR, so again, the first thing is the same. The changing now that we have to calculate Q and R, and we find the Kx based on the LQR, and all the remaining is the same. So this is the closed loop, this is the eigenvalue of the system, this is the BR, this is the closed loop, and this is the closed loop of the system, and this is the initial condition and the unit step response. So all the difference is just we calculated based on the Q and R. Now I put too much weight on the state, not on the control action. So if I hit the run, you can see this is the system, and this is the tracking, this is the original, which is okay. Now you can see this is the new poles of the system, 3 poles of the system. Now you can say like change the system to not stable. So now the system is unstable. We can check. So this is the system unstable, and here. So this is the regulator, and this is the tracking for the unit step. Now we get to the end of this video. I hope I can see you.